notation. You can write it as an indigo, right? Think of it as an indigo like this. Some operator, right? Psi naught, and then d tau, which is the volume that you have to integrate over. And this operator, right? What is this operator? Operator is just a mathematical operation. An operator is essentially your electric field, right? Because you're talking about photon, right? The photon coming in, there will be an electric field interacting with the dipole of your system. Okay, so I can write a little electric field vector dot r, right? R is the R, if you like, I just write it loosely. R is, if you like, is the along the dipole, right? Think of it as the dipole element of your system. And E here is the electric field vector. So this contains the information about the photon, right? So it depends also on the polarizability as well. So basically this is, if you align your photon axis, your polarizability axis with your dipole field, this is just approximately equal to R, really, right? Because you can take out the vector out. So basically what you got is essentially I proportional to some indigo, right, of this state, little r psi naught d tau, like this. And, and all squared. We're talking about all squared. Okay? So the intensity would be proportional to this indigo, right? So you can think, it's easy to think about. We don't worry so much about the math detail. The way to think about it in quantum mechanics is quite logical. We are just thinking about a transition. So from the initial state, which is the ground state psi naught here, to the final state. And the final state is the ionic state, size of A. I choose A because that's happened to be the first excited ionic state, A state. And to make this transition, I need some operator. And this operator is, of course, the dipole operator, because I'm interacting, I'm sending in my electric field. My photon field is an electromagnetic field. So I'm electromagnetic field interacting with the dipole in my molecule to give me an operator. So that's how we think about it in quantum mechanics, right? And then this gives me the magnitude, and the square of that will be the probability, right? Remember, in quantum mechanics, we cannot really see wave function. We can see the probability of wave functions. So you can sort of square, and that gives you the intensity. And now you picture that instead of talking about one wave function, you can picture wave function in a certain vibrational state. So you treat it like the vibrational wave function here, and you're talking about the overlap. Sometimes people call it overlap between the initial state and the final state. And that gives you these little peak height intensity that you see. Okay, so the calculation, indeed, you can calculate ionization cross section theoretically without too much problem. There's still difficulty in treating this operator simply because the magnitude of the problem. Because you have all these electrons, right? All these electrons to think about. And then you have to think about vibrational profile as well. You have to think about as a function of distance and different potential and so forth. Okay?
Is it quantized or is it
interpretation?
Say that again?
The interpretation of the intensity though.
The interpretation of the intensity is the probability of seeing the full electron from there. Right? So you look at the peak that you see here, right? So you would say that you have higher, you would see the probability of seeing that electron is higher than this. And what does that mean? It means that if you think about the wave function, right? So here's what I'm trying to draw. The wave function overlap of this state with some of these states are more favorable to give you this higher intensity. Okay? So it's a transition probability. Right? The intensity represents transition probability from the ground initial state to excited state, and the transition probability depends on the overlap of your wave function. So here I draw the two vertical lines so that I can see that, okay, I'm starting with ground, the electronic wave function, which look like this, which look like a little bump like this. I'm now trying to overlap this with all the upper state, because when I do the integration, whatever outside this zero here, I will get nothing, because I'm multiply them together, right? So therefore, I'm just overlapping this, appropriate with the appropriate scaling factor, this due to this R, with any of these guys up here, to get my intensity, okay? So they correspond, in short, they correspond to transition probability, okay? Okay, you have a question?
Are these vibrational energy states quantized?
Yes,
It's not.
it's definitely quantized. I mean, this is why we need to study quantum mechanics, because it is a quantized state, of course. Because that is why you have discrete energy level for each vibrational state. And of course, on top of these vibrational states, if you're talking about free molecule, for us, it's not so important because we are talking about solid and surfaces. But for free molecule, you also have rotation. So on top of these vibrational state, you also have rotational state. And what does the quantization of rotational state means? I hope you guys remember your molecular spectroscopy course. What it means is that when you rotate, you have a certain frequency, right? That's what quantization of rotation means. It's quite interesting because when you vibrate, you have a certain vibrational frequency, and you vibrate in a certain way, certain arrangement of vibration. So you can't just, free vibration. You can't just have the atom moving around in any different way, and that's what's controlled.
How do we distinguish? Because when it is overlapped, it looks like a continuous function.
Which I don't follow. What overlap?
The previous graph, the one which we showed.
Yes.
Yes, the top one. Yes.
Yes.
It's an overlap of all those energy states, right?
No. Each of these P, right? Let's say, sorry, let me just go Y. Go back here. Let's say this going to this state, right? This corresponds to one P of this bump, this big envelope here. There's an envelope of P. So when I go from this ground, the electronic ground vibrational state, to one of the excited vibrational state of my A state, of my ionic state, I will see one of these P. One of these. So that gives me a P. Now this you see a little ends here, that's due to instrumental resolution. Right? If I have infinite resolution, it will be delta function. It will be like this. It will be just a one line. And that's just due to instrumental resolution. I can't resolve that. That's why they have P merged together. Okay? So that's why a lot of the material chemists and chemical physicists are still working on for electron spectroscopy in a big way. There is a X-ray and UVV, VUV physics conference to be held in Vancouver this July, and this is the first Canadian conference being held in Canada this July. We talk about all these fine effects, and if people are interested, I can give you some information about this. The website is open. I was involved in organizing this meeting. So there's a lot of interesting things, emerging things that occur already for electron spectroscopy, and there's people still talking about it. But the emergent new machine, which we'll talk a little bit about later, this become a very exciting field in material science, in biology, and in physics and astronomy and so forth, right? In terms of understanding this electronic vibrations spectrum like this. So let me continue here about this plot. This is sort of a very fast course of revealing spectroscopy for you. And here I have